Thank you, Lisa. And I'd like to first start to thank the Bowers for conceptualizing and putting to this great museum, and to Lisa and the entire History of Diving Museum staff for doing such a great job. This is, I think, my third time speaking here, and probably my sixth time visiting the museum. I count twice today because I looked at it yesterday and again today. But I want to thank you all for attending, and for those who are on Zoom. So the first question I want to pose to you is, that's me on a camel in a desert in the middle of Dubai. And what does that have to do with the intersection between the diving sciences and diving? So I'll start off by asking that question, but keep it in the back of your mind because you'll figure that out as we get more into the lecture. So my background is a physician who has had the distinct privilege of working in emergency medicine and undersea and hyperbaric medicine for over 30 years. And throughout that 30-year period, I've had the honor and privilege of taking care of injured divers, treating them in hyperbaric chambers, seeing them in my dive medicine clinic, doing fitness evaluations, return to diving after diving injury, having really a privilege to teach at the United States Coast Guard Academy to the Coast Guard cadets in their NAUI diving scuba program in some concepts in dive medicine and dive safety, and having had the privilege and honor of lecturing at the Naval Undersea Medical Institute in Groton, Connecticut, to the undersea medical officer candidates in dive medicine and dive safety, as well as lecture and also do research. I've been a volunteer researcher with Divers Alert Network. So I thought I'd kind of put all that together in a sort of a summary of the intersection between the diving sciences and diving and how this all relates. But a quick pitch to my podcast. I'm a host of a podcast called Fitness and Diving, and I have 14 episodes of discussions and conversations with diving medicine experts, physicians, expedition leaders, and dive safety people. I'll drop some names: Fabian Cousteau, Dan Orr, Doug Ebersol, to name a few, and conversations on about all aspects of fitness to diving and what some of these expedition leaders had to do after they've had some significant medical issues that they had to recover from so they can maintain their fitness in diving. And most recently, I had the privilege of being interviewed for a podcast with Joe Kokoza, who hosts the Diver TV series, and he's done over 250 episodes in diving. So it's a pretty impressive catalog, and he's ongoing. So if you can look him up, he's on YouTube, another great podcast. But this one was sort of a 50-minute podcast, video podcast on fitness to diving most recently. So today, what we're going to do then is talk to you about the intersection of the diving sciences and diving, and we'll do that through a historical perspective of diving. We'll talk to you about how we perfect the science of asking the question in science. And if you ask the wrong question, you get the wrong answer. Now, if you ask the right question, you may not get the answer you're seeking, but you'll get an answer. So it's all about understanding what is the question we need to ask, and we'll develop that theme part of this discussion today. And we'll go over some of the advances in science and technology and some of the challenges, and the many challenges in diving science and scientific discovery. And then I'll share with you some of my real life experiences as a volunteer dive researcher. So when we think about the concept of outer space and then the concept of inner space, it's all a function of the atmosphere, from sea level to below sea level to up in the stratosphere. And it's a function of the principles of the gas laws and how those gas laws affect pressure, volume, and temperature from zero sea level to up in space to below sea level, deep under sea, or even in a hyperbaric chamber. And what are the effects of pressure, volume, and temperature at the different areas between outer space and inner space? And all that affects us as divers, right? And those concepts are real. And when we think about then the diving and diving science, diving technology, and dive safety, we have to take a step back and look at the origins of diving. And we can see the earliest recording were those of diving for mother of pearl in 4500 BCE. They were diving for pearls, food harvesting, and these dives were free dives. They were 2 to 3 minutes at about 20 to 30 meters. So pretty interesting, many centuries ago. And then during war and commerce, in 400 BCE, the Persian king used divers to salvage goods. First used a diving bell by Alexander the Great. The military uses included cutting anchor cables and boring holes in ships and building and destruction of harbor defenses. And then some of the exhibition here in this museum happened to correlate with my presentation. Described the tympanic membrane. 1800, Leonardo da Vinci sketched a diving appliance with a wine bladder. And then it was Edmund Healy who devised a method to replenish during dives. And this early rendition of a diving back BC era, it was a surface air trapped in the bell compressed by water pressure. It was used for salvage, and think about technology was known in the science of diving at that time and how much danger there was to those who were in this dive apparatus. Nicely featured here in the museum is the left bridge contraption that he designed in 1715. It was a self-contained atmospheric device that he used for salvage work, where he obtained tons of silver, many Dutch shipwrecks. And then the diving suit by Klinger in 1797, first UV suit, and there was no thermal protection, and it was, so you had poor visibility, a lot of leaking, a lot of air embolisms, a lot of people that didn't so well from a physiology perspective. And then it was the CSS Honey, a submarine during the Civil War in 1864, became the first submarine to sink a ship. So pretty impressive use, although the submarine itself had sunk 3 times. Each time it sunk, some of their submariners died, but they couldn't figure out why. On the very last voyage, and the entire crew died. Never really sorted out. And what it turns out that the consensus is they died of CO2 intoxication, because as they're exhaling water under pressure, the CO2 is building up, probably all became unconscious. But this is one of the examples of technology outpacing the understanding of the physiology and the ability to deal with the consequences, right? We didn't have a lot of understanding of the gas laws or the physics, physiology, and the physicality of diving, and yet they died in unexpected death. They couldn't figure it out, but when we have that technology now, we can sort of come to a conclusion as to what happened. And we think about the issues related to tunneling. The Hudson River Tunnel in 1889, the construction workers digging the sand, they were referred to as sand hogs. And as they were underground, on pressure, sort of contained vessel, and they were under pressure, dry, right? And as their atmosphere pressure was increasing, they started to develop some symptoms of decompression sickness. It was referred to as caisson disease or the bend when they came to the surface. And there was a high mortality rate when they were building these bridges and tunnels because the physiology was not quite well understood. In fact, there was a theory that we could treat these caisson workers in a hyperbaric chamber, but there was a concern that oxygen was toxic at the time, and the initial treatments for these caisson workers in a hyperbaric chamber were treated on air, further compromising their physiology. And it wasn't until much later in the century when they figured that oxygen is actually a good thing and is not toxic and actually will help offload the excess nitrogen that was building up, causing their caissons disease. So again, science and technology were not quite coordinated at the time. And it was in 1956 that Jacques Cousteau wrote this book, The Silent World. And this was a really fantastic book at the time because it featured his crew, his diving expeditions on the Calypso when they were doing their diving expeditions and scientific discovery. And what was so fascinating about the book, we sort of take it for granted. Right now we have Facebook and social media, and we immediately get instantaneous review and understanding of any scientific aspect going into space, NASA, etc. But in reality, in those days, you could only read about these things in books and articles, in the news, or on radio. And you would listen to this and grow fascinated by the technology that it allowed them to dive deep. And when we think about Jacques Cousteau as a scientist, he really wasn't a scientist, but he was starting to ask the question, can humans stay underwater for extended periods of time? And what are the benefits? What are the challenges? And what are the risks, right? Those are scientific questions. So he's starting to formulate the right kinds of questions and then have to discover what those answers are. And to accomplish his many tasks, he had to devise technology that will allow him and his crew to get in the water, go underwater for deep periods of time, and be able to come to the surface with minimal risk. And so he developed early scuba gear that would allow him to negotiate those difficult tasks. It was also Cousteau and Link and many others who asked that question, can we sustain life in underwater for a longer period of time? And he developed these underwater habitats. It was in 1962 that Cousteau and Link had that concept. They conceptualized it, developed it, and then Cousteau had Conch Shelf 1, where he had 6 men. They were called oceanauts, underwater aquanauts, if you will, breathing nitrogen, oxygen for 35 feet for 7 days. So he was able to start to answer those questions. How long? What are the risks? What do we need to mitigate those risks? And it was 1964 that Lincoln Lambertson developed an underwater habitat that went as deep as 430 feet. And it was Cousteau developed a second underwater habitat where he had 7 oceanauts for 30 days at 36 feet. And they were able to go out from their underwater habitat and then dive deeper, as deep as 330 feet, but then come back to their resting state at 36 feet and survive and be able to come to the surface without having the significant issues of decompression. And this is sort of a classic picture that you get on the, and it features Cousteau, his crew in the habitat, his wife Simone with her back to us, and featuring cigarettes, light bulb for flashes, and lots of booze, so that's how they were able to treat themselves appropriately. And then the military had taken that same sort of scientific approach and asked the question, when we have missions underwater for deep times, how do we do that comfortably, and how deep, how safe? And so they asked those questions. So Sea Lab 1, in 1964, they had 4 US Navy divers that were underwater at 192 feet of seawater for 10 days. They studied things like the physiology and psychological endurance being underwater in an isolated area for that period of time. And Sea Lab 2 had 3 teams of 10 men at 205 feet of seawater, and they had spent 15 days at a time underwater. And they started to augment the staff with astronauts. And Scott Carpenter was one of the first astronauts to spend 30 days in the underwater habitat. It was Sea Lab 3, the third rendition of this, with the idea that we have to go deeper for longer. And at 600 feet of seawater, one of the divers had a seizure, presumably because of an oxygen toxicity seizure, and he passed away. And immediately the Navy had a reflex reaction. We scrubbed the mission. We're not going to do this anymore. We're putting our divers at great risk. And so after Sea Lab 3, the underwater habitats were put on hold for the longest period of time. And when we think about habitats, these underwater environments where divers can sustain working for longer periods of time, there were civilian renditions of this where we would saturate the diving scientists so they could stay underwater, under pressure for prolonged periods of time. Lab in the Bahamas and the Caribbean between 1972 and 1985, and then Aquarius in St. Croix, where there was a hurricane and damaged it at one point. It was brought to the surface and refurbished and brought here to Isla Morada, where Mission 31, that we'll talk about shortly, was obtained. And so the Aquarius habitat is still in the water. It's no longer active. And it was the grandson of Jacques Cousteau, Fabien Cousteau, who in 2014 put a team together and had some donations to try and resuscitate the Aquarius Reef Base. At that time, it was owned by the National Oceanographic Atmospheric Agency. It was in disrepair. It needed additional work. They weren't willing to get any further. And so Florida International University assumed sort of management responsibilities of Aquarius Reef Base, but it was a very expensive proposition. So Fabien Cousteau, part of Mission 31, was trying to get funding for a 30-day mission extended to 31 days. And the reason Fabien Cousteau wanted a 31-day mission is because his grandfather had a 30-day mission. So he wanted to be 1 day more than that, so Mission 31. And the scientific questions asked and answered during this 31-day mission were looking at things related to climate change and the related challenges of acidification. It was looking at things like the effects of microplastics in the ocean, also the decline of the biodiversity. And this was a scientific venture between 3 universities, including Northeastern University, the Massachusetts Institute of Technology, and the Florida International University. Here is a cutaway of what the Aquarius reef habitat looks like. On the far left, there's basically racks or beds for 6 scientists, divers. In the middle portion is sort of the kitchen area, and to the right is actually their science exploration discovery room, as well as a shower and a bathroom overhead. So kind of an interesting thing. And what made it interesting to me was I happened to work with Fabien Cousteau on a other project, and he invited me to join him during Mission 31 as a VIP diver. So on day 21 of the 31-day mission, I got the opportunity to dive on Aquarius Reef Base and spend a couple of hours on Aquarius Reef during a live mission during Mission 31. And so that's myself and Fabien Cousteau in the kitchen area. And I was only inside during the live mission for an hour because I couldn't stay too long because I would overwhelm myself with nitrogen. And behind me is this beautiful portal where there's barracuda diving around and this really unbelievable experience. I'm talking to Cousteau right across from me, and they said, okay, now let's do an interview. So now I have to spontaneously come up with sort of an interview, a discussion with Fabien Cousteau. On my left, I'm watching the barracuda swim by. On the right, I have the cameras, right, because they're videotaping this thing. And in front of me, I have Fabien Cousteau, the grandson of Jacques Cousteau. So it's kind of a surreal experience, but a really cool opportunity. And we know that next month you'll feature a discussion from the deep, the Vanguard. This is a portrayal of what that underwater habitat eventually will be, but it's now live, it's underwater. And Tom Potts, he actually was part of Mission 31 at that point. Will give you further information about further opportunities for understanding. But when we think about those questions, formulating those questions, it applies to all kinds of divers, public safety divers. There must be some unique issues related to public safety diving that puts them at risk. So we need to be able to ask those questions. And what about technical divers, deep divers penetrating 2,000 feet in caves and caverns? And what are the questions we must ask to maintain the safety with all the new advanced technology and or exploration and technical divers. Now, this is I would have to say, qualified a technical diver. Mixed gas diving, have to switching gases, long decompression times, right, putting themselves at great risk. What are the scientific questions we need to understand so these divers can go deeper, longer, yet come to the surface and be safe? And in our military application, right, there's got to be some questions. Now, in the picture on the bottom left is a diver is doing what's called a high altitude, low opening. So at 35,000 feet in a non-pressurized aircraft, he's going to jump out of this plane, parachute out, do a free fall dive and jump, and then deploy his parachute, hit the water, and then dive underwater to accomplish a mission and attack. What could go wrong, right? And you have this SEAL delivery vehicle left upper. So these are SEAL delivery vehicles that are attached to submarines. So a submarine at 1,000 feet will deploy this SEAL delivery vehicle. The divers will deploy underwater, acquire a target, complete a mission, and come back to the submarine. What kind of physiology, what kind of medical fitness is required to do the tasks of a military diver? Those are the questions we ask. And then when we look at deep exploration, we have things that, to date are unapproachable by a human diver, right? But we have technologies that allow us to go deeper and longer. And here at the museum, you see a number of these one atmosphere suits. So these suits can allow a diver to go underwater, under pressure at great depths, at great pressures, and not have to necessarily decompress over time because they're bringing on excess nitrogen. But because of the composition of these instruments to prevent the pressure from caving in on them, right, they're very immovable, right? So you can't really function really well. And when you get a chance, and many of you have already been into the museum, you'll see those very features. So we have submarines. We have apparatus that can get you under pressure for great depth. These have explored as deep as the Titanic. And we also know that if you ask the wrong question, or if you ask the right question but refuse to listen to the answer, right, it could end up in a catastrophic failure. And this is the Titan. And we also know that we mentioned the sandhogs in 1898 building tunnels and bridges. Well, we're still building tunnels and bridges, and we're still understanding the issues related to tunnel medicine and pressure and treating those injured sandhogs. And these are the current diamond head cutting tools that are used to cut through. And in these areas, the pressures are immense pressures, and they have the same increased risk for getting decompression sickness. So these sandhogs currently are using current technology and current science to minimize the risk for them getting caissons disease and decompression. And even medical applications, right? So when we look at hyperbaric chambers treating medical conditions for diabetic foot wounds, for example, or hearing loss, there's all kinds of medical rationale and reasoning why hyperbaric chambers can be effective. And if you apply them with all the current science and knowledge, it's done in a safe manner. But if you use these same medical treatment chambers, but you aren't understanding what the risks and the benefits are, that potentially can lead to catastrophic failure. And there have been a couple of incidents within the United States in the last year and a half where two hyperbaric chambers were treating individuals for medical. Both led to catastrophic failure, fires, and unfortunately, the inhabitants passed away. So we're thinking about ultimately understanding the gas laws, and we aren't going to give you a lecture in diving physiology and diving physics, because you'd probably walk out if I started, so we won't do that. But I will share with you an understanding of, since we're talking about diving and we're in the history of diving museum, the traditional classification of bubble formation. And it's a function of, as you are going to descend underwater under pressure, as you're increasing pressure, what's happening is the gases will increase in what's called the partial pressure of the gases. And we know that if we're at sea level, we're breathing 21% oxygen and 78% nitrogen. We remember that probably from high school, some of us anyway. But as we start to scuba dive or dive, the gas laws will say that the partial pressure of the gases increase. So nitrogen's going up, and that nitrogen can go into our cells, and those cells, once we come to the surface, the gases come out of the cells and we can get decompression sickness. So decompression sickness is a combination of decreasing the atmospheric pressure and getting that nitrogen gas and going into circulation, and we can get then decompression sickness. Could be bad. And so the understanding then is that when we look at the signs of decompression sickness and or the possibility of something called an arterial gas embolism, it can give us symptoms that can be very fatal to divers or have permanent injury and risk to the diver. In addition to these bubbles that are coming out of solution, there's a lot of inflammation, a chemical cascade, if you will, and that causes the long-term effects of decompression sickness. And it was back in the early 1900s, 1908, where Haldane was commissioned by the Navy to look at injured divers, military divers, and develop a method to decrease the risk of getting decompression sickness. And he had to ask the question, how do I develop that methodology? And what he did was he did mathematical calculations on what the relative risk based on the depth and time that you're underwater. And based on that, he would develop something called the dive profile to suggest for the time that you're down for that depth, what you need to do to come to the surface to minimize that risk of getting decompression sickness. So it was a calculation that has basically been the foundation for all the dive profiles that we're basing our diving and dive safety on currently. However, there are so many derivations of that because despite following all the rules and the calculations of a decompression profile that Haldane developed in 1908, people still get decompression sickness. Following all the rules and calculations, why? That's the question. And so there have been many diving scientists that have developed thoughts and newer calculations and possibilities as to why that is occurring. Workmen and others have developed other tools and methods, and they've integrated all these methods into a computer where we wear on our watch, which can calculate the stress that we're getting at depth, the amount of nitrogen that we're acquiring, and how much time we spend underwater and what we can do to help mitigate that risk. And despite all that, we still get divers who get decompression sickness. So there are lots of questions, but we don't have all the answers yet. And that's kind of the interesting part of diving science and diving technology, where we continue to ask those questions to minimize that risk. So when we think about currently, there are calculations that are built into algorithms which are built into our dive computer. And actually in your History of Diving Museum, you have a great feature which has about 30 different older dive computers. And as that technology keeps improving and the theories and the scientists develop newer concepts to mitigate risk, there will always be the risk of getting decompression sickness. And so how can we mitigate or lower that risk? That's sort of the importance of what we do in diving sciences. And the other part of all this is that we have to also appreciate that it's important that we foster and develop the young children, the young adults in science, technology, engineering, and medicine. And I had the privilege of working with a group of 8th graders who they were tasked with their STEM project to develop an app that divers can use to determine what their relative risk for decompression sickness is, that it could give them in a negative feedback loop so they can have that in real time as they're diving to decrease their risk for decompression sickness. Now, when I was in 8th grade, I was thinking about playing baseball and maybe, cutting out of school, right? but I wasn't thinking about developing an app. But this is the importance of promoting science, technology, engineering, medicine in our youth, right? And it's kind of brilliant as to what these kids were thinking. This was not something that I offered them. This is what you need to do. They came to me and said, this is what we're doing. Now I need a dive physician to review this with me. It's pretty impressive stuff. So one of the things that I've done as a physician, I've had the opportunity to volunteer my time with Divers Alert Network. And as a dive physician who's also a diver, I'm also a DAN Referral Physician, a DAN Instructor. I have given a lot of lectures and have worked closely with Divers Alert Network. And one of my dreams when I was much younger was to be a scientist, but I couldn't because I was a dive physician, a doctor, emergency medicine doctor, and I don't have time to do science. But as a volunteer, I was able to do that in the latter part of my career. And so fortunately, I had the opportunity to go to North Carolina and spend a full 10 days with Divers Alert Network, where they kind of taught me the important aspects of diving sciences and what I need to do as a field researcher. And then I had the opportunity over the last few years to participate as a volunteer field researcher with Divers Alert Network. So I want to share some of that information with you because I think it's pretty cool stuff. So one of the things that happens for divers are when there's a diving fatality, and that's a statistic none of us want to be a part of. The research suggests that there's about a 28% incidence of cardiac events associated with a diving fatality. So that's a pretty high risk. And when we think about a cardiac risk, as we get older, right, our cardiac risk goes up, right? Our age, we get deconditioned, we might have some obesity, being overweight, diabetes, hypertension, elevated lipids, might smoke cigarettes, and there's that family history. So as we see older divers are diving much older, of course, that cardiac risk goes up. So what Divers Alert Network have done in their research department is look at and develop cardiac studies in divers and looking at those risk factors and ways to mitigate that risk, identify the risk. And many of these studies, and there are many studies that they have done, are done in conjunction with Divers Alert Network, UNC Chapel Hill, Duke University, and the University of Maryland. And these studies looked at trying to ascertain what is the risk for the different types of divers. So recreational divers have a different risk than a military diver, right? A scientific diver versus a commercial diver. So the studies were pretty interesting. That's me on the far left doing an echocardiogram on a diver at Mystery Lake in South Carolina. And the studies were to get these divers into waters, technical divers in this case, put them to about 70 feet and keep them there for a period of time so they can accumulate nitrogen, and then bring them to the surface, do what's called a deco stop and bring them to the surface. And before they went in the water, we would do baseline testing of various inflammatory markers. Remember I said decompression sickness is inflammation. So if we can see what your baseline inflammatory markers are, so you shouldn't have any, we put you in this stressful situation. As you come to the surface, nitrogen comes out and causes inflammation, and we measure those markers. And then we also look at other things like your vital signs, whether you're getting any symptoms of decompression sickness, and whether you're accumulating any nitrogen. Can we measure the nitrogen? And then in addition, we also want to develop technology, wearable technology that could be used underwater, sort of like when you were in NASA up in space, but underwater, where we can monitor your heart rate, your blood pressure, your stress levels, maybe even the ability to monitor in real time your bubble production or the nitrogen that you're off-gassing as a sign of inflammation. So that's what this study did. And we would acquire the data, get a baseline vital signs. We'd put the diver out into the water in a reproducible manner. So at Mystery Lake, there's a dive platform. The route is routine. The divers have to be all technical divers, so they have to be good divers. They have to have required to be medically fit by a physician to participate in the study. They couldn't have had any diving 7 days before this dive, so there wouldn't be any question of any mitigating factors. And as they came to the surface, we would start to do an ultrasound to see if they're developing any bubbles and if they're having any symptoms, and does that correlate to any of the blood, saliva, urine testing to looking for those inflammatory markers. So kind of neat stuff. And I wanted to share you this video. This is one of the ultrasounds we did. And what happens is when we come to the surface as a deeper dive, right, and the nitrogen comes out of our cells into solution, it goes in our blood and it circulates around. And depending on where those bubbles go, you can either exhale that, that's fine, that's what you typically do with those excess bubbles of nitrogen. But sometimes those bubbles of nitrogen may be deposited in your arteries or part of your body, and you get the symptoms of decompression sickness. But it's going through the blood. And here's an example of the nitrogen going through the heart. And you can see on the left side, that's the left side of the heart, those are nitrogen bubbles going from the atrium into the ventricle. Now, this is one of the divers who came to the surface but had no symptoms at all. He wasn't having any signs of decompression sickness, was perfectly fine. So just having bubbles or off-gassing lots of nitrogen doesn't necessarily mean you get decompression sickness. But if one of those bubbles happen to go in a vulnerable area, you can get decompression sickness. So one of those mysteries, the questions of why. Why does someone make a lot of bubbles but don't have decompression sickness? There's another person who makes minimal bubbles and gets decompression sickness. Is bubbles the issue? Is a lot of bubbles the issue? Those are the ongoing questions we have to continue to ask. So we also think about then, we talked about technical divers, what about public safety divers? Well, in the United States, public safety divers, many of them are volunteer divers. They work in very stressful situations in zero visibility in cold waters in either rescue or recovery mode. So this is, you know, tough conditions when you have to do that work. And if you're a volunteer diver and you're older, right, what's your cardiac risk? It goes up, right? So we have to understand then, are we able to assess that risk? Public safety divers train for these really tough situations. We call those stressful situations. So they'll black out their visors, their scuba masks, so they can't see. They'll get them entrapped in some apparatus. They'll be pressured to escape from this situation in real world order, right? Because stress. So imagine if you had some underlying heart disease and you were in a real world situation with zero visibility, what could go wrong, right? So now this is, again, pool sessions, but also done in real scenarios. I've had the privilege of working with a number of public safety dive teams in the United States. This is at the Mid-Atlantic Public Safety Diver Forum. So it's a 5-day workshop, 3 days of in-water and 2 days of lectures. So as a volunteer research with Divers Alert Network, we recruited public safety dive teams. This is a dive team from the Newtown Underwater Search and Rescue Team, so from Newtown, right? And that's on the left is the Danbury, the Divers Alert Network team. Myself included. On the right is a Newtown Search and Rescue team. And we don't dictate what their dive profile is or what they're going to do on a given day. They do their thing. In this case, they were doing tandem dives, so 2 divers at a time, going out at 25 feet and going for evidence recovery. Seems pretty straightforward. Volunteer team. The oldest diver is 64 years old, right? Fit? We hope so, right? Cardiac risk? We hope not, right? But what are those variables? So what we did in this case is we would evaluate these divers. We would do a series of vital signs, and we would get a 12-lead electrocardiogram, echocardiogram, and again, get that data to determine what is the risk. And what about a risk for a deep dive, expedition dive? This is Richie Kohler, who has the really, phenomenal author. You've got a couple of his books out on the shelf here. But he's been to the Britannic, USS, the HMS Britannic at 450 feet. And that's pretty deep on rebreathers, so very technical dives. And he has agreed to and participate as a volunteer participant for Divers Alert Network to come out to his expeditions so they can study deep dives, and they do the same thing. They're doing actually additional to evaluate cognitive functioning at depth and during the various deco stops, as well as the physiologic functioning and also wearable technology. So again, we're gaining more data from public safety divers, technical divers, and lobster divers here in Florida, and military divers. So the next part of this is to understand the concept of something called functional capacity. And this is something I'm very interested in. The definition is the individual's capacity under controlled conditions to perform tasks and activities that are necessary or desirable in the lives, and how well someone can perform a task under ideal or near ideal conditions. So we're in a room right now that's a pretty near ideal condition. Temperature is pretty controlled, there's good light. But what could go wrong to these safety divers, right? Because they're not ideal conditions. And in scuba diving, you need a certain degree of physical fitness required for safe diving. And every type of diver needs a different degree of physical fitness. You need aerobic capacity and cardiovascular health and lung function, and the ability to perform the physical task underwater. So the question is, as a scientist, can you assess functional capacity, and how far can you push a diver in extreme conditions? Extreme conditions can be something for a recreational diver that's unfit at 10 feet in warm water, right? That's a challenging situation if they're not well trained or well qualified to do so. But we have sort of these marathon athletes, right? You're in space, and the question in functional capacity is really vital. And when we think about then issues that occur in diving or in space, tasks and task loading. A task load is a measurement of human performance that broadly refers to the level of difficulty an individual encounters when executing a task. And that task loading is the accumulation of tasks. So we know that when you're a diver, if you're task loading, so lots of things happening at once, you tend to make errors. And if you're doing it underwater, under pressure, warming up, and your visibility is going down, and now you have a problem with your regulator or your buoyancy, and your task loading is increasing, things can go wrong. So task loading is a cumulative number of mental and physical tasks the diver needs to manage simultaneously while underwater. And the increased risk of mistakes occur as you have overwhelming tasks and complex tasks and managing equipment and unexpected situations and environmental challenges, right? And managing task loading requires proper training and dive planning and buddy communication and prioritization of tasks. So we're getting there, why I was on a camel. I promise you, okay? So I had the privilege of being asked to participate as a volunteer researcher with Divers Alert Network. They were asked to participate in a study with the Department of Defense, and they were looking at something called functional near-infrared spectroscopy, neurocognitive monitoring in divers. That's the name of the study. And I have to read a disclaimer, I'm required to do so, that the material is based upon work supported by the Department of Defense, small business innovation research program under contract, and any opinions, findings, and conclusions or recommendations expressed in this material are those of Divers Alert Network and do not necessarily reflect the views of the Department of Defense. So I've made my disclosure. And here is that device. So near infrared spectroscopy. And what this device does, it measures the difference between oxygenated and deoxygenated hemoglobin in the superficial capillaries in the skin. Who cares? Well, maybe if we get enough data, it has an ability to measure functional capacity and how far we can push a military dive. Remember, this is a Department of Defense study. And what they want to know is how far can I push this diver beyond the limits because he or she has a mission to accomplish, right? And when do I need to say, hey, your functional capacity is impaired, we're done, get you out of the water. So this device measures this, it attaches to a computer while the diver is diving at great depths. This was tested in a wet pot. A wet pot is a bathtub in a hyperbaric chamber. They put the diver with this equipment on in a wet pot, and they pressurized the chamber to 145 feet to see if this device works. And it did in a hyperbaric chamber in that very controlled condition. But that's not good enough, right? We need to know, will it work in the real world situation? So we want to put the same diver in 140 feet somewhere. Where do we go? The other part of this is that we need to assess their functional capacity in addition to monitoring these variables that are coming out of the brain waves, if you will, or the blood flow. So they assessed memorization and speed and risk-taking by these handheld devices. They almost look like a tic-tac-toe puzzle, but they actually measure functional capacity, memorization, speed, and risk-taking evaluation. So now let's go a little fast forward to why I'm on a camel and why am I talking to you about this? Because the place to test a diver at 145 feet in a safe environment is in Dubai, at Deep Dive Dubai. So the dive team flew across the pond and went to Dubai. And that's us in front of Deep Dive Dubai. Deep Dive Dubai is one of the deepest pools in the world. It goes to 210 feet depth. So it's a beautiful pool, and it has uniqueness because it's deep. So when you think about if you're doing dive research, do you want to put someone at 140 feet, like at Mystery Lake in North Carolina, where the visibility isn't so great, temperatures vary, it could be raining, it could be cold, or do you want to go in a relatively controlled environment where you can control that variable? So that's why we chose Deep Dive Dubai. Now, Deep Dive Dubai is a really awesome place. You can get training, education, lessons, both free divers and technical divers and recreational divers. They have many features along the way. You can sit and play pool. You can sit in a Mercedes. You can just have a great time there. So part of the study was to recruit participants. All of the GUE instructors at Deep Dive Dubai all agreed to participate as a study participant. So they're all well-seasoned technical divers. That's what you want, to do something in a safe manner. We spent a lot of time educating them about what this study was, talking about the risk and benefit, having them sign an informed consent, and then training them how to do those testing devices. And we did a medical screening and a pre-brief. We had to make sure that they really understood what the risks and benefits and alternatives to doing human research. And then we had to really talk to them about measuring their functional assessment, making sure that they can understand to use those devices properly. And then we had to get them hooked up. So they're in the water. We're putting these electrodes to the scalp. We're going to then use this computer on the side and get them to a depth, and we're going to then have assess their functional capacity at depth as the nitrogen levels going up and they're in 140 feet of water. We also want to assess whether the device is actually usable at 140 feet. Is it going to fall off the head? Will they have any side effects or risks to it? Each diver was accompanied by a safety diver and technical diver, one of the DAN divers that we were with. And here they're all set to go. So kind of neat, right? Imagine diving around here with this. You'd be the you know, really cool stuff. And that's that computer attached to the diver. This is attached on a D-ring. And now once the headgear was attached and the computer was about to be used, we would have to calibrate the computer to the headgear, right? To make sure it's in sync. And then once that was done, we would then have them come down to a ledge only about 5 feet below water, where they would practice their little handheld device to make sure it's functioning, that they got that okay. And then we would have them go down to 145 feet on a platform. We have the safety diver who's making sure everything is done properly and safe. There are no issues. And then they're getting nitrogen accumulating. They're under that stressful environment, and they're assessing their memory and risk taking. After that's done, then they ascend to about 20 feet, where they're then, or you can watch them underwater as they're trying to negotiate that, right? Pretty cool stuff. We'd bring them to 20 feet on a ledge, put them on 100% oxygen to help get rid of some of that excess nitrogen, and then reassess their hand skills and their risk taking and all that. At the same time, continuously, this device is monitoring 1,200 variables on a continual basis into this computer. And then when you get to the surface, we have to kind of get rid of all the equipment and then look for any side effects and complications. Now, one of the risks or complications we saw is these little pucker marks from the electrodes. We also noted that we had women divers as well that didn't have shaved heads. So the electrodes couldn't really adhere well because of the hair. So that would be a challenge, right? If you're going to be a military diver and push, you can't have any hair, right? Because you wouldn't get good acquisition of data. Now you have this side effect, right? Due to this, the good news is within 5 minutes it dissipates. Again, this is the data that we're acquiring. So complications and side effects of any research are really important, right? And then the military needs to decide on, is the device used? This is an 11-pound weighted object, right? Now your military diver has already got 80 pounds of other gear. Is it really practical? Is it too big? Do they have neck pain as a result of this? Is it even functional? So I'm asking all these questions, and to be honest, I don't have any answers, because my job is to be the objective scientific taker of information, but it goes to someone else to kind of analyze the data. All the data that I have been involved with Divers Alert Network for the cardiac studies, that's a study that's been going on for 3 or 4 years. Those studies are now complete, and all that data is now being evaluated by the science team. So I can't even tell you what that data shows, right? But that data should be helpful in answering those questions, whatever those questions are.
What gas were they breathing?
They were breathing air. So what we've done then is talk to you about this intersection between the diving science and diving, right? We've looked at the historical perspective of diving. We've talked to you about perfecting the science of asking the question. We've talked to you about some of the advances in science and technology and the challenges, and I've shared with you, at least from my perspective, some real life experiences. So with that in mind, I want to thank you for your attention and open up for any questions that you might have.
Question?
Sure. So the question is that when we're doing the research and we're getting things like electrocardiograms, echocardiograms, not everyone who's acquiring this data are even physicians. They're ultrasound technicians, you know, or students or other volunteers. So the answer is, if I saw something that was bad, as a physician, I would say that's bad, right? And we need to do something. And this actually happened where one of the divers came and his blood pressure was really elevated, right? I couldn't, in good conscience, let him dive, right? He was really upset because he drove 4.5 hours to participate as a volunteer diver. So we had to, you know, tell him you can't dive. He got treated for it and did well. We, on echocardiograms, if the sonographer sees something that's really bad, would have to mention that, but it would have to go up the administrative chain to decide what has to happen. Any of the electrocardiograms that we did, we didn't, at least that I was evaluating, we didn't see any major abnormalities. Yeah. Yeah, so a couple of things. So anyone who was a bubble maker who had a positive ultrasound, we would have them come back every 20 minutes until all bubbles were no longer to be recorded. And sometimes it could be, you could be there for 2 hours, right? Every 20 minutes until everything's dissipated. So they're all continue to off gas. At that same time, while they're there in real time, are you having any symptoms? No, no, no. Vital signs are good. So at the end of all the bubbles are gone, I'm asymptomatic without symptoms, then they go home. Now, what Divers Alert Network and UNC are doing is they're taking all of the ultrasounds and applying these ultrasounds using AI technology to be able to sort of screen and scrub these ultrasounds to determine what the relative risk is and how it evaluates the amount of bubble production. And there are a way to score the amount of bubbles. So, you know, high score means lots of bubbles, a low score means a few bubbles, right? And the science suggests that the more bubbles you make, the more likely you are to get decompression sickness. Goes without saying. But none of the participants in any of the studies that I'm aware of, at least the ones that I've been involved with, have had decompression sickness or admitted to it. Yeah, and so the question is that, you know, in your experience, previous training, there's a device that you could wear, and it can help elucidate whether you're making bubbles or not. You can wear them. That technology is now wearable now, where divers are using that in real time while they're diving. So as they're ascending, they can kind of hear that they're making lots of bubbles. That might be a signal to them to sort of stop at that level, right? Maybe go back down a couple of feet, a longer decompression stop to minimize the risk of decompression sickness. But what is also known is that there are certain people that are bubble makers. In other words, they will produce a lot of bubbles at even minimal depths and not get decompression sickness. And there are others that may never make bubbles, but one day get decompression sickness. So it's still a question that has needs more questions, I guess, right?
Did you have to ride?
I've been diving for a long time, and I found this fascinating because even the history that we have been doing for a long time, you touched on some different things we didn't have. It was really kind of cool to see you. I don't know whether you put it in on purpose because you saw the Lethbridge barrel and you just knew, but it was really nice to see a lot of that.
The funny part is I walked through the museum yesterday, and I said I need to change my slides because, you know, and then I'll just keep it as it is.
You did, because you had Klinger, you had
Right.
several different times. So thank you, Dr. Sally, as well. That was really fascinating. And I know that you came through twice because you've been here for a couple days, but we would like to thank you with an annual membership.
Oh, thank you.
For you and Joan. So you can actually come back 362 days, but I do not want to take you from any missions or any trips to Dubai.
Got it.
So anyway, thank you very much. He's going to be around for a little bit if you have some more questions. We also, the History of Diving Museum has got guided tours this Saturday. So if you're around, normally we just have self-guided tours and get a ticket meander, but on Saturday at 11 and 2, we're going to be doing guided tours. So come on down. We also still have the Blue Star Museum program going on through Labor Day, which allows active duty military. It's free every day, but an additional 5 family members. So that'll be going on through Labor Day. I think we have another question through Zoom.
Yes.
Okay.
Do you anticipate any conclusions that will alter today's safety guidelines for recreational divers?
The answer is, I think, possibly, because even though, let's say there's a Department of Defense study or a study that relates to technical divers, right? A diver is a dive, right? The risk is the risk. And so that can be applied uniformly across all levels of diving. So I think that the more information is entertained about any class of diver will really have application to all divers.
Thank you
All right,
again.
thank you.
Great.
Thank you all for attending. Thank you.